Hi everyone, in this video we are going to discuss photovoltaic cells in the context of incident radiation from the sun. Okay, so we just want to figure out, is it possible to actually harness the energy or harness that incident radiation that's coming from the sun and use it and convert it into electrical energy? And we're going to do this by talking about photovoltaic cells. So let's start off with a very basic definition. And the first thing I want to highlight is that a lot of times people will just call these PV cells. Instead of photovoltaic, they say PV. So just be comfortable with both pieces of information. So now what a PV cell is essentially it's a device that converts light energy, which we know is our incident radiation from the sun, to electrical energy. So now a PV cell is something that works very well, or it's a great energy option for remote locations. So think South Africa, some places in Mexico a lot of times, even Alaska, places that they don't have a lot of energy or can't easily access electricity very easily. Photovoltaic cells actually provides that to them. It gives them a way to get some electricity just by using the incident radiation from the sun, which is really cool. And so maybe out of all that context of everything I just said, you're thinking, I think I've heard of these before, but I call them something else. Yes, colloquially, these are often referred to as solar cells. So if you hear solar cells, they're talking about photovoltaic cells. It is just a more common or a lower level way of just talking about it. So please, if you can, try to call them photovoltaic cells because you'll just sound more educated and you'll also make me very happy. All right, so now you probably have used photovoltaic cells on a daily basis for years and years and years, especially if you're a student, because a lot of times those calculators that are powered by solar energy use photovoltaic cells. They don't just use one, they use about 3 or 4, it just depends on how big your calculator is. But what they do is they stack the photovoltaic cells right next to each other and they are able to harness enough energy to power your calculator, which is great. But now, that's a calculator. That's something that's teeny tiny. What if you want to get enough energy to turn a school on, the electricity at the school on, or something of that sort? What you need to do is make something much bigger. And so let's start very simply by looking at this upper left-hand corner when we're talking about cells. Okay, so over here, so we start off with a photovoltaic cell. This is one individual cell. What they then do is put them from the cell, they take one cell and they hook them all together to create what's called a module. All right, so if you can see, they start here at the bottom, and then they have a pathway where it's going up and then down and then up and then down and so on and so forth. So they connect all the photovoltaic cells into a module. From there, what they do is they put all the modules together to create an array. Now, the arrays can be a variety of different sizes. A lot of times they are custom built for whatever the purpose is. So I'll show you a couple examples in a second and kind of highlight that in a second. But just know that array is not always a 4x3 space, not always, just for this example it is. So you start off with a single photovoltaic cell, right? So you're converting light energy to electrical energy. Then you hook a bunch of photovoltaic cells together to create a module. Then you take your module and put a bunch of modules together to create an array. Your array is what you put outside, okay? Let's look at 2 examples here. The first one is if you put these arrays on a roof. So this example I have is literally just on the roof of a building. And what you can see is they're not completely flat. These arrays are not completely flat. They're slightly tilted, okay? They're trying to maximize the amount of solar energy that's coming in and actually interacting with these solar panels, okay, or these photovoltaic cells. You want to make sure that you maximize that energy. You would never want to have a solar panel turned away from the most spot or where you're going to have your highest amount of energy, your sunlight. Alternatively, and this is actually more common, this is called a solar park. And now this one that I've highlighted right here is from Bavaria, Germany, or Deutschland. It's a very beautiful place. I actually really tried to visit this one time, but it didn't work for me. I'm so sad. But anyway, this is a solar park, and so what they have are a number of different arrays, and they're all stacked up, and they're pointing in one direction. I want to highlight that. If you can see, all the arrays are basically facing us. We're looking at it. They're not all in different directions. They're not flat. They're all facing one direction. So now, what I want you to do is use your brain and try to figure out what direction do PV cells face in the northern hemisphere. Yeah, that part matters. Northern hemisphere. Think about it. You want to maximize the amount of sunlight. Are you facing north, south, east, or west? Only 4 options. Talk it out if you're not sure. Go. All right, did you get an answer? Hopefully you did, but if you didn't, that's okay. I completely just asked you this out of thin air, so I don't really expect you to know the answer yet. But the correct answer is south. So in the northern hemisphere, whenever you have a solar park like that, you want to do everything you possibly can to make sure that your PV cells or your array of PV cells are facing in the southern direction. And that is because that we have done so much research and we figured out that in the northern hemisphere, that's when the PV cell actually acquires or is able to grab the most incident radiation. Okay, not north, not east, not west. Now, if you think about this, in the southern hemisphere, it has to be the exact opposite. So if we had a solar park in the southern hemisphere, we would make sure that all of our arrays are facing in the northern direction. Okay, so make sure you're very careful, make sure you're clear about that in your head. It has to do with the incident radiation. All right, so now, how does this actually work? Well, you have a PV cell, so you have a photovoltaic cell, and we know we have incident radiation coming in. So remember, energy is equal to Planck's constant times frequency. So now 3 options can happen. The first 2 are not very advantageous, okay? The first one is if it just passes through. Okay, so it's not absorbed. That's option 1 if it passes through. The second one would be if it's reflected out. So that's option 2 if it's reflected. Also not very helpful, right? Passes through, reflected, that means we didn't actually grab that energy. It just hit the cell and left. The third one, which is the important one, is if it's absorbed by the PV cell. So absorbed. So this is option 3, and I would say this is the best option, and this is really the entire reason why we do it. If it didn't absorb the energy, we wouldn't be studying PV cells. Now, how does a photovoltaic cell actually absorb that energy? Well, PV cells are made up of semiconductors. Okay. So now semiconductors, if we've already talked about, so if you recall, we can have them just be a plain semiconductor, so a pure element, something that is usually, that would be with silicon, so just pure silicon sitting there by itself in an elemental state. Or we can add some elements to it. We could make an N-type semiconductor, or we could make a P-type semiconductor. The P-type is usually when you've added an element that has 1 less electron than whatever your elemental semiconductor is in. And then your N-type is usually when you've added some kind of element that has 1 more electron than whatever your original semiconductor is. Okay, so but in order to have a PV cell, you definitely need to have an N-type and a P-type semiconductor. You need both. Otherwise, you're not going to be able to absorb the energy here like we just discussed up at the top. All right, so now let's look at an actual example of this. Here is a single PV cell with 1 N-type semiconductor and 1 P-type semiconductor. So what we can see from this side is that we have our sunlight come in, and it is absorbed immediately. And so what happens is we get this flow, this beautiful flow of electrons, and they always are moving in the same exact direction. So they come in from the bottom like this, and so we know electrons have a negative charge. Well, as soon as they experience this hole, which is an absence of a negative charge, so really it's kind of like a faux positive charge, that negative is immediately attracted to it. So the negative just zips right up, it tries to go up to the proton, then as soon as that, or up to the hole I should say, as soon as these electrons move, whenever they move, they leave behind a spot that is now an absence of charge. And so what happens is you get this beautiful cycle, and you get this, all these electrons just cycle, cycle, cycle. And so you're actually able to take light energy and convert it into electrical energy. So you've created a current, which is awesome, using an N-type and a P-type conductor. So now this is if you just have 1 of each, 1 N and 1 P. So that's the top one here, what we're looking at. That's just what we looked at. Now, the second diagram that I have here is called a multi-layer solar cell. So that's down here. That's the second one. A multi-layer solar cell is something that has a combination of P and N type. So this is 1 P and 1 N type semiconductor. This is several P and N-type conductors, and they're stacked one on top of each other. So it's P, N, P, N, P, N, over and over and over again. But as you can see, each one of these layers are about 15 micrometers thick. Okay, so they're teeny, teeny, tiny. And just for a frame of reference, this third picture down here at the very bottom, that's actually a human hair. And so that's thickness is 50 micrometers. So these layers here of your P and N-type conductors are significantly smaller, 3 times smaller than a single human hair, just to keep that in the back of your mind, okay? Now, why are we looking at these different ones? Well, a single single layer solar cell is about 15% efficient. So a commercial single layer solar cell is about 15% efficient. However, if you stack all of these P and N type semiconductors on top of each other, you can actually increase the efficiency to 72%. Okay, that is ludicrous. It is so crazy. We can increase this to 72% efficiency. Now, I just want to note that instead of several, you need 36 P and N type semiconductors stacked on top of each other to get 72% efficiency, but it is possible. Recall, a coal power plant is like 33, 35%. Everything else is just terrible. So here is an option. This is a real viable option of how we can do or how we can extract our energy in the future without contributing to global warming, without putting carbon monoxide into the atmosphere, okay? This is the future.